We're excited to have you here and excited to get started. Joining me today as a co-host is Shannon Dew, who is also a sales engineer at Cockroach.
Hi, everyone. Nice to meet you.
So yeah, let's jump in. Fairly simple agenda today. We're going to talk about payment systems in general, kind of what are the challenges that are common to all payment systems, and then we're going to talk a little bit about how does Cockroach work and how does it operate in such a way that meets those challenges? And then we're going to dive into fraud detection, which is a little different than we've done in previous webinars around payment systems, but we're going to kind of focus in on that one particular area within payments. And then we're going to do a little bit of a demo showing kind of how fraud systems can work in Cockroach. So um, yeah, so we can jump forward.
Yeah, so on this picture, I think it's really apparent that Jim and I do a few things other than just talk about Cockroach DB. Really, we've been coworkers for several years, but we're also friends. We bonded over playing guitar, and if you see on the left, Jim Hatcher in high school playing his trusty Les Paul, and on the right, you see me a little bit more recently, and we wanted to ask you guys, which one of us is out playing rock and roll shows in 2026 and never really maturing or growing up, and which one of us has matured to play and sing fine Italian songs. I think there's a clear choice here. Moving on a little bit though, we'd like to jump in and talk a little bit about both of our journeys and how we kind of arrived here at Cockroach DB.
Come here. I'm gonna clear my dog out of here. Come here. Sorry about that, but my dog wanted to be a member of the webinar today. Um, yes, I just wanted to talk about my career journey kind of in general terms. I think this probably matches a lot of people's career journeys. But early on in my career, kind of coming right out of college, getting my feet under me as a programmer and as a data analyst. I worked on relatively small systems and I worked on line of business apps. We might have megabytes of data or gigabytes of data. And so kind of early on in my career, I did SQL Server. I was doing .NET development. Before that, I was doing like classic ASP development and some Visual Basic, things like that. And SQL Server was awesome. You can use it. It's kind of like the Swiss Army knife with databases, I would say. The database was great about enforcing consistency and all the things that you want your database to do and not have to worry about you in your code. And then as I got to working on bigger and more complex systems in my career, I hit a scale ceiling with SQL Server where I just can't get a big enough box to do what I need to do. And so I kind of made a shift at one point into working with Cassandra. And I went to work for DataStax, which is the company behind Cassandra. And I worked on really large systems and really loved Cassandra in the sense that it scales kind of as big as you need it to. And it's very fast and but it comes at a big trade-off. A lot of the things I used to let the database do for me around enforcing ACID and enforcing referential integrity and doing joins and things like that, you can't do that in Cassandra. There's this big trade-off between consistency and scale. And so I've been at Cockroach now for 5.5 years, and uh, I think Cockroach was really appealing to me because I loved relational database and I loved the ability to scale, and I hated having to give up things to do that. So, it's kind of been my career journey. It's kind of how I came to Cockroach, and in this journey, maybe right about the middle, I was working at some payment companies. I worked at a company called First Data Corp, which is now part of Fiserv. And I worked at I did some auction payments at a like an eBay auction payment company, and I worked at Western Union doing money transfer. And so kind of a lot of the scaling challenges I hit in my career kind of, in, that zone. So anyway, that's me.
Yeah, my journey is a little bit more unconventional and meandering, I suppose, to arrive at databases. We jokingly call this my journey into madness. I started writing code when I was a kid, when my mom won a Texas Instruments computer that you would plug into the television, and it came with a big manual that you could program, basic into the computer. But when I was around 14, my high school math teacher challenged me to take a computer science 101 course at the local university. And I ended up ruining the curve for everybody and getting pulled onto a research team. And I started playing around with neural networks and stuff like that in the mid 90s and doing C++. plus plus. And I just wanted to be a coder and knock out C++ plus plus all day long. And in the early 2000s, I went to work for, and during that led to me basically working for a credit card processor, a competitor of First Data, TSYS, from 96 to '02, where I got exposed to, large scale payment systems using, COBOL, JCL, database, everything that you could possibly do on multiplex, mainframe systems. And, got into the world of online credit card applications and statements when that just started to emerge. And, if it touched the payment life cycle, I probably worked on it during that period of time. And I jumped over, though, working for an insurance company. You guys probably, in the US anyway, heard of Aflac, where they had a famous duck to do commercials. And there I got exposed to a different kind of financial systems with claims and underwriting and premium payment systems. And got sucked into doing data architecture there and did that for about a decade. And, I got to work with SQL Server and Oracle and Teradata and a lot of different systems, and eventually went into consulting and got exposed to financial systems in a wide variety of retailers, travel companies, large auto parts companies, places like Home Depot and General Parts Company and things like that. And but ultimately got to see the journey of the payment all the way from the point of sale all the way to reconciliation and reversal, fraud detection, so on and so forth. So took a little bit different path. And for the last 2.5 years, I've been working at CockroachDB, kind of exploring and evangelizing distributed databases here. Go ahead. So we're going to talk about payment systems and some of the demands on those. Payment systems have a combination of requirements that, really make them challenging to implement. First of all, they can have a very high data volume. For example, Visa processed $12.3 trillion in credit card payments in 2023, and that is trillion with a T. But as a payment system, they need to do more than just handle average volume. It has to be able to handle peak volume, for example, like retailers on Black Friday, and payment volumes spike to a level that's several times that of the average. And especially during those peak periods, many payments are processed every second by the system in real time. So fast response times, low latencies are critical when customers are standing at a point of sale terminal or and waiting for their credit card to be approved or declined, or waiting for confirmation after clicking a buy button on their shopping cart. So their system has to process many payments concurrently with response times that are measured in the milliseconds. Payment systems also need to operate across multiple countries and jurisdictions and regulatory boundaries. And this adds a challenge when you're trying to deliver fast response times and low latency and ultimately a great customer experience, because round trips to a centrally located system adds problematic latency in payment systems. And additionally, payment systems tend to be highly regulated with different rules based on geographies and jurisdictions that impose additional requirements on data storage mechanisms and processing and where data is domiciled. Adding to that, downtime can't be tolerated, nor can data loss be tolerated. So it has to be available at all times, and the payment data always has to be present in order. Any blips in availability means, unhappy customers and brand impact, lost sales, market basket turnover type of things. And even brief delays in processing can be interpreted as downtime with any kind of a retailer. And so addressing this challenge requires, redundancy and high availability, especially when storing data and processing it. And so if one part of that processing system fails, something else has to step in and heal and ensure that the processing keeps going. So data has to be backed up and made highly available to recover from not only disasters, but just blips in performance, whether it's a natural disaster or some sort of human cause. Finally, there's an assumption throughout all of this that consistency and correctness of the data is non-negotiable. These are table stakes. So the system has to make strong guarantees that the data constraints and the relationships that are always preserved, no matter the data size or the load on the system. So recording a payment typically requires updating multiple data locations as a single transactional unit, and that it must guarantee that other concurrent transactions can't interfere or undermine the correctness of that data. And so that's a long list of challenges. During my 6 years at TSYS and near a decade at Aflac, I grappled with challenges like that on a daily basis. Next slide, please.
I think when I think about what is the poster child for the transactional workload, I think payments to me jumps to the top.
Yeah.
It's like it's got all the things, all the tricky things.
Yeah, it has all the flavors of challenges with working with data and ensure, in particular data correctness. And I think as you scale, having that data correctness is a unique challenge that we try to address in particular here at Cockroach. Um, I think another one of those things that is unique about the modern payment application is that you have different types of data and require a lot of flexibility that maybe we didn't require 20 years ago. I mean, most everything was normal row store data, or you even had stuff stored in vSAN files and various data mechanisms that were involved in payment systems back then. But now you're dealing with a multitude of data types, and Cockroach DB in particular gives you, as a developer, the flexibility to have strongly consistent SQL, to have JSON data, to have spatial data, and now even have vector data in the same database tables working alongside, so that you're not transporting that data and piping it to different databases or different mechanisms for different data types. And this gives you the ability to have one database and one source of record, one system of record as a single source of truth. So you reduce some of that complexity and overhead and operational complexity that comes along with building a data store for a modern database or modern payment system, excuse me. So moving on just a little bit here, I want to get into some of the technical challenges, and obviously, Jim, feel free to jump in at any time. We both have different experiences with payments, but there are some technical things that I think are kind of table stakes for working with payments. Like, you need zero RPO, like we talked about, and very minimal RTO. So you need to guarantee zero data loss, but you need recovery from interrupted transactions in seconds. You need the ideal of having flexible deployments. So 10 years ago, I would talk to somebody and they would never think about putting, a database instance in the cloud, for instance. But we have the flexibility, or we need the flexibility in a payment system to be able to deploy in the cloud, on-prem, in a private cloud, in a hybrid environment as somebody's in a kind of a nascent cloud modernization journey, to deploy in Kubernetes or to use a managed service even. To have scalable CDC, where every authorization and settlement and reversal is streaming reliably to other engines and other data stores and other systems. The ability to do normal operational maintenance like schema changes and upgrades without taking the database or the tables offline. I remember carrying a pager and doing database changes between 2 a.m. and 4 a.m. and losing sleep, all while having small children at the same time. It was pretty miserable. I think, minimizing that impact to your operators is extremely important. Having something like a familiar SQL interface, and in particular in this case, like Postgres SQL compatibility, wire protocol compatibility, and syntax compatibility, and working with a lot of the common Postgres extensions, being able to work with that, I think, and have a common interface and not some sort of specialized language, is very, very important. And then legacy database kind of feature parity, like with legacy RDBMSs, having transactional guarantees and familiar SQL semantics that you can rely on, I think are extremely important. And then having the ability to domicile data and have declarative data placement so that you can put data in jurisdictions where it needs to be, you know, say it needs to be housed in a particular place due to GDPR or DORA or something like that. Or you want to bring data closer to the users for a better experience with latency. Having that capability is extremely important. And as with all financial transactional systems, enterprise grade security and meeting the requirements of PCI DSS and SOC 2, being able to do that, I think these are all kind of the foundational things you need from tech underlying a payment system.
And this is a slide we've used in past versions of this webinar, just kind of outlining what does a payment gateway look like, what does a payments processor look like. So I think when we talk about payments, sometimes we're talking about the core companies like TSYS or First Data that are giving that layer of where they're processing everybody's payments either through a gateway or through a low level processor. But sometimes we're also talking about the merchant and the system that they're using to actually interact with these lower level things. And so um, we have depicted here a fraud service that maybe the payment processor is using, but later on in the talk we're going to talk about like a fraud service that you could use as a merchant, while integrating, but just as kind of talking about kind of an architecture that you might see in the payments world.
Yeah, and I think the key thing to note on that slide, and you don't have to go back really, but just the ideal is that, we're depicting that, Cockroach DB is, it can be that single source of truth for all of these things, whether it's the actual payment gateway or processor or a downstream, fraud risk engine or something like that. You can have that same reconciliation, that same settlement, all of that happening off of the same source of truth in a distributed type of model.
Yeah. Yeah, we do have big payment gateways that use us as the back end and need to achieve that kind of really large scale, and Cockroach is great for that.
Yeah. So how do we work? Let's think of Cockroach DB as kind of a cloud native SQL database that was architected and built from the ground up to solve three main problems of scale, resiliency, and data consistency. Cockroach DB again, it presents a familiar PostgreSQL interface. Data gets split up into tiny segments and gets automatically distributed across a cluster. The system automatically rebalances and heals and re-replicates data as you add or remove nodes when you're scaling or scaling up or scaling down. That design lets you scale horizontally, so you can add nodes on demand to increase throughput and capacity, and you can also scale vertically, if you want to add CPUs or go to bigger boxes. But you can do all of that without the need for, manual sharding schemes that you deal with in some of the more legacy databases that are out there. And it handles that complexity for you, and it reduces a lot of the bottlenecks that you have operationally and with, providing the throughput that you need for your users. Because all the writes are coordinated by consensus, and CockroachDB implements like true distributed transactions with serializable isolation and asset guarantees. You get immediate consistency, strong consistency everywhere in the cluster. And at the same time, CockroachDB is built to survive failures. So you could lose a node, you could lose an availability zone or a rack, or you could lose an entire region or data center and still survive with zero data loss and have automatic failover across those machines and regions. So the ideal of the cockroach is the ability to survive anything, and that's what we do with the database. For geo-sensitive apps, which most financial and payment systems really are, you can domicile data close to the users to improve that latency and user experience. In addition to the regulatory reasons that you might do that, and you're still maintaining that global correctness in one logical database. Put simply, Cockroach gives you a single managed, always on SQL database that it scales like the cloud, it survives like the cloud, and it keeps your data correct so that you can move quickly to implement new features and business functionality without trading away the reliability or consistency of a more traditional SQL database.
Yeah, and I think you might look at this list and say, well, lots of database providers say they do consistency or they do resiliency, but NoSQL providers might say, hey, we're really good at scale and resiliency. And something like an Amazon Aurora might say, I'm really good at data consistency and resiliency. But I think what's really hard is doing all of these. And we can talk about a little bit more why, but I mean, Cockroach, to me, the magic of what Cockroach does is we can do all three of these really well at the same time.
Yeah, absolutely. It's Jim and I both seen a lot of database platforms and systems, but having this all in one kind of package, it's a big claim, but we have hundreds of customers that are doing this successfully and doing it at extreme scale. You see here, why Cockroach DB for payments and some of the things that we've talked about already before we launch into kind of fraud detection with Jim here. But I think that Cockroach DB can be, and it is currently with a lot of our customers, the foundation for a modern payment system. In payments, worst case scenarios happen all the time. Outages during peak traffic. Take Black Friday again as an example, or failed settlement jobs or updates that interrupt authorizations. CockroachDB is really designed to keep running through node, availability zone, or region failures, and your transactions continue and data remains intact. All of the nodes are identical to each other. You're not bottlenecked by a single leader node or gateway node. In that case, everything is equal to each other. And as your transaction volume grows, you can simply add nodes. It scales without that complexity of sharding or disruptive migrations, and you can add capacity to it as you need it without pausing that live traffic. And I've talked about this several times, but I don't want to undersell the importance of data correctness and strong consistency. Strong consistency matters in payments, authorizations, refunds, settlements. They all rely on accurate, up-to-date data, and CockroachDB ensures that those decisions are made against a single correct view of the ledger, so to speak. It's built for high write throughput and it supports zero downtime upgrades, which does increase your operational efficiency. And one of the things that we've kind of hinted at is the multi-region capability. We're multi-region capable right out of the box, and that the security requirements that we've tried to comply with has made us very popular with financial services institutions. I think 40% of CockroachDB installations are in some sort of financial services or payments scenario. But I want to, pause there. I've talked a lot about, what we do and how we do it, but I want to hand it over to Jim so he can talk a little bit about the fraud detection pattern and what we've seen using CockroachDB.
Yeah, thanks, Shannon. So I wanted to just kind of define what a fraud detection service looks like. And specifically, I'm looking at like a card not present scenario where somebody's ordering online or on a phone or something, or they're not like swiping the card through the machine at the Kroger, checkout line. So you have a fraud detection service, and it has transactions that come in, and those transactions have a little bit of information. They'll have some kind of an ID and the credit card information, an amount, maybe some buyer info, um, maybe a device fingerprint where there's something that tries to identify that device, whether that's a browser or a phone. IPGO where it says, okay, I can tell based on where the information in the browser, I can tell you're coming from a certain part of the world, and then the card authorization results, and that all gets pushed into the service, and that's typically not enough information to make a good decision. It's not enough context. So, what a fraud detection service does first is it does a bunch of enrichment. It says, okay, I need to go back and using these incoming variables of credit card number, buyer, phone, email, device, etc. What can I go back and look at contextually that's happened around those things in the past? So it creates what are called velocity variables, which are things like how many times has this card been used in the last 60 days? How many cards has this buyer tried to use in the last 30 days? How many times has this been associated with a transaction that later came back as a chargeback? And so it creates all these velocity variables, and there might be some other lookup data that you do to just enrich this with as much relevant information as you can. And then there's a set of rules and or models that get applied. A lot of times there's a data science group that's developed scoring models, and often there's like some just basic rules that say, okay, I don't need to do a lot of complex math. I can just look at a few things and say this is approved, this is declined. And so all those rules and models run, and then you kind of you develop a decision criteria. You say, okay, based on the scoring that I got from those models, I'm either going to approve this transaction or I'm going to deny this transaction, or in some cases, I'm going to maybe do some further review. It's in the gray area, and maybe there's some human review, or maybe there's some further systemic review we can do to it. Kind of depends on your business model. If you're shipping something out and it doesn't go to the next day, you might sort of do a quick approval, but in the background you're doing some further review. So that can work a couple different ways. But then, so once you have the decision, you save it, and then you return your response back. Um, and then there's kind of this out of process loop where your issuing bank sends you chargebacks. So you say, hey, that transaction you did 62 days ago, with this ID number and this credit card number, that person called the bank and said, that wasn't me, that was fraud. And so that chargeback gets fed into you, and that's how you kind of know, what was good and what was bad. And typically people can do chargebacks up to 90 days after the transactions occurred. So you typically won't see, chargebacks from, 60 day or 6 months or a year ago, but getting that chargeback information is a really important part of the process. So that's the general idea with a fraud service. That's what it's doing. And so when you think about how do I operate a fraud service, you have your clients coming in. You probably can scale out your fraud service by having multiple instances of it, putting a load balancer in front of it, and then having a back end, a database. And so it's relatively easy to scale the app layer because it's stateless. It's often more challenging to scale the database layer. So you start doing things like, okay, I'm gonna have a standby database. If the hardware in my first database goes down, I'll have this standby. And then you say, well, I really need to have a whole nother region. What if my whole region goes down or my database goes down and this whole region can't operate? I really need to have another region somewhere else where I've got apps running and a load balancer, and I've got another database there and another standby. So you often see this type of scenario where maybe you have an active region at the top and it does a synchronous write to a standby database, and then it does like an asynchronous write to a database on the other side. And so that gives you the ability, if the top region goes down, you can fail over to the bottom region. So you see that a lot with relational databases. But I think where the challenges start to come in are, okay, what happens if the size of my database can't handle the throughput of what I'm doing? I just can't respond to everything fast enough. I can scale up my app layer, but it's harder to scale up the database layer. Um, what if I need to do downtime? My database, I need to do some index maintenance, or I need to do some upgrades of the database. When can I take that downtime and not affect my service? And then you get into consistency issues. What if the data I've written to one side and there's an asynchronous write to the other side, and the one side fails, and where does that leave me in terms of RTO and RPO? And what if I want to run active active? What if I want to run applications against both sides? And if there's an asynchronous eventual consistency part going across the regions, what does that mean for the correctness of my decisions? What do I do if there's a hybrid deployment and I need to run part of this in the cloud and part of this on-prem, or part of this across different clouds, or if I'm trying to put the services close to where they're being consumed? These things all become issues, and they're all live in that database layer. So, Cockroach kind of solves a lot of these issues just with its kind of basic architecture, which is that we keep multiple copies of the data and allow for horizontal scale. So if you need to increase throughput, increase scale, you just add nodes. By default, Cockroach runs in a strongly consistent mode. So if I write something to region one and I get an acknowledgement back, I'm guaranteed to get the same thing back in region two if I went and did a read. And we use the RAF protocol to enforce all that. And so you get scale, you get consistency, you get resiliency. Cockroach, we need a quorum of replicas available to be able to read and write. So you can do things like doing upgrades. You can take down a node, do an upgrade, bring it back up, continue to do a rolling restart to the cluster, and you can do that while the cluster's up and running. You won't lose the ability to read or write any data. So this is kind of the core thing that Cockroach is good at, and it works really well in these fraud systems. Um, and I just want to touch briefly on some AI topics, just because they're obviously a huge thing right now. Um, one of the things Cockroach supports is vector search, and vector is kind of like the lingua franca of AI. But we have an implementation of PG vector, which is a so with PG vector we can store a vector data type in a table, and if you create an embedding, you can store that embedding within your table, and then you can do things like you can compare an incoming fraud transaction that's looking to get a decision made. You can convert that to a vector, and you can compare it to the existing transactions, kind of like we did with velocity variables, and say how similar am I to something that was a chargeback, or how similar am I to something that was clearly a good approval. And so vector search is an interesting piece that you can incorporate. Um, and I think one of the most interesting things we've done with vector is we've built vector indexing that is meant to work in a distributed model. So we're not dependent on really fast memory speeds because our data might be spread out across lots of machines in a big distributed system. So we have this vector indexing that really does a good job of making vectors be OLTP speed, even across really large vector spaces. Um, and I think maybe skip past this because I'm trying to get to my demo here. But um, basically, Cockroach has done a lot of work to try to make these vectors very fast and very compact in terms of how much data they store. So a lot of neat stuff we're doing there. And then in terms of kind of where vectors and AI things could be incorporated in fraud systems, part of that enrichment we're doing early on could involve a vector search, and then later on when we're saving the transaction, we could generate embeddings for this one transaction coming in and make sure we save those back into our vector indexing. Um, and you see a lot of work in fraud systems where the orchestration of how the flow within the system works is agentic. So, agentic AI is very good for making decisions about okay, I've got all these microservices in place. Each one does a specific thing. I can do some good reasoning about I'm going to call microservice one and then microservice three. And then I can skip the others because I have enough to make a decision. So there's some neat stuff that can be done there with orchestration. And then I think even for like the review cycle, like you approve some things, you deny some things are going to be reviewed. There's some neat stuff that can be done there with agentic AI reviewers to kind of dig down another level into transactions that need a little further exploration. So all right, so I'm going to do a demo. Let me stop my screen and I guess share the whole thing now. Um, okay, so Um, I'm running a Cockroach DB instance here, and I'm looking at what we call the DB console. And so this is a cluster that has 6 nodes. You can see they're in US Central 1A, B, and C. I have 2 nodes in A, 2 nodes in B, 2 nodes in C. So six total nodes. Each one of these nodes has 8 vCPUs and I think 500 gigs of storage attached. And so I've written a simulation that kind of does the database work that we talked about here in a fraud simulation. So let me switch over to that. Um, let's see. Okay, so I got the simulation. This is a tool we use called DB Workload, and I wrote this fraud detection Py, which is a Python script. It just kind of defines kind of what I want to happen when I kick this off. But it's going to connect to my cluster, and so I'll start that off. And it'll start to run in the background. I told it to run 32 threads and to run for a duration of 300 seconds, so it's about 5 minutes. And so while it's doing that, I'll just quickly show you a glimpse of what it's doing. So the first thing it does is it writes into a table called card transaction, and it generates some random things. It generates an amount and a random card number and a random buyer email and a buyer phone and a device fingerprint, all this kind of input stuff. It writes that into this card transaction table and saves it in a pending state. And then it goes and it calculates some velocity variables. So as an example, it goes back and looks and says, what other transactions have a buyer email that's the same as the buyer email on this transaction within the last 30 days, and I want to get a count of that. And then it stores that result, and then it says based on this current card that got used, what's the total amount of orders that have been done using that card in the last 90 days? And so these are just some examples of things that we might want to see in order to make a risk decision. But other things like how many, give me a distinct count of cards that have been used by this same buyer. So you can imagine if one buyer uses 50 cards to make transaction, that seems a little suspicious. So it goes through and it in this simulation it does six of these velocity variables and calculates those, and then it makes a random decision whether to approve, decline, or review, and then it saves that back. So if I look at my console here, we can see um, these are some metrics. So I can see the number of queries coming in. So what we see at any given point, this is doing around 1,000 inserts per second and around 1,000 updates per second and around 6,000 selects per second. So that kind of lines up with what I was saying. We do an insert, we do six selects, and then we do an update. So one business transaction, one fraud request takes 8 queries. So we're seeing a total about 8,000 queries per second. And so that's counting like the database level stuff. And we can see the service latency. This is the P99 service latency. So the P99 for these is around 14 milliseconds and staying pretty flat there. And we can look at our cluster. We can see across our 6 nodes, we see the CPU usage is hanging out about 50%, maybe a little as high as 63%. So we're pushing this cluster pretty hard, not super hard, but kind of a median workload. And then what's cool about Cockroach, what's fun to do with Cockroach is I can go and stop a node. So let me stop node 3. So I've got of the 6, I'm going to stop node 3. And we'll watch what happens. Um, so the first thing I expect to happen is instead of seeing 6 live nodes, I expect one of the nodes to show up as in a suspect state. Let me just refresh this to speed it up, maybe. Um, so we're starting to see here some under-replicated ranges. Under-replicated means I expect to have 3 replicas available, but I only have 2 available. So I can still operate with 2 available, but it's kind of a warning state. So okay, so here this node 3 here just went into a suspect state, and up here we see 5 live nodes and 1 suspect node. So this is kind of a warning state, like we've taken a node down. Maybe that was an unplanned thing, or maybe it was a planned thing. Um, but Cockroach is still able to run, and we can still look at the metrics and see that there was a little bit of a dip in throughput and a little bit of a spike in latency, but we're still up and running. So anyway, so that's a general idea. Cockroach, we get the name Cockroach from the fact that it's a highly resilient database. It's a database that's hard to kill, like cockroaches. And so this is something that would be very hard to do with a relational database, but it's just kind of something that's par for the course in Cockroach. So let me stop there. Want to make sure I leave a little bit of time for uh, questions. Are you seeing my screen?
Yeah, you go to slideshow mode. Yeah, there we go. Let's jump. I want to highlight one of the things that Jim just called out there in his demo. He talked about this could be a planned or an unplanned outage, with that node. We talk a lot about disaster scenarios and unplanned outages, but one of the unique things again about Cockroach is that you can do things like do upgrades, do schema changes, upgrade the actual OS, and do network patching and so on and so forth like that while the database is online due to that redundancy and that replication. So in the same way that that node went offline, you would continue to serve reads and writes. Some of the key takeaways as we wrap up, I want to revisit just a few things. First, again, scale, consistency, and resilience are non-negotiable foundations for a payment system. These are basically table stakes for any successful payment systems. You can't afford to compromise on those things. Um, you know, CockroachDB is very powerful in that regard. We're zero downtime, disaster recovery. We're active everywhere, or active, 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 multi-active, like I like to say. Meaning your operations, again, they continue seamlessly. And again, simplifying your architecture to be able to give yourself a unified data view and plane for your transactional payment data that you can simplify your fraud detection and all of these processes, whether it's fraud or authorizations or whatever, in one data plane. And you can combine again that vector and that transactional data in one table in single queries, so on and so forth, and take advantage of that distributed vector indexing and search there. The data placement policies that we talked about for data domiciling again allow you to host data in the specific areas that meet regulatory, compliance reasons, as well as for latency and user experience reasons. And, again, for the future of payments, and then, agentic workflows and fleets of agents, payments are going to be continually be influenced by agents and the AI movement. The power to scale and to meet that growing potential fraud risk is essential. And so giving yourself a foundation to be able to scale easily and without the complexity of some of the manual sharding schemes is essential. In short, we're trying to give you a platform for modern payment systems that's going to grow and evolve as payment systems evolve. If you go to the next slide, we have a couple of QR codes. If you scan the one on the left, you can get started with CockroachDB Cloud or Managed Service and get $400 in free credits. If you'd like to talk further, I know there have been some great questions in the Q&A. If you'd like to talk further with, somebody like myself or Jim or our colleague Alex, who's on the call as well, you can scan the one on the right. I'm going to move ahead to the last slide here, and we're going to open it up for any further questions. I think there are a few that are popping up here.
Yeah, Artem's asking would it be better to do velocity calculations using a processing system like Spark, Kafka, Delta Lake. And yeah, there's certainly different ways to do that. I mean, you could maybe have a caching layer that sits on top that's doing very fast reads. As long as you have some kind of a mechanism to keep that in sync, or I've seen some systems where as soon as you log into a website, they start calculating velocity variables behind the fact, knowing at that point kind of hey, you've logged in, so I already know your email and your phone number, or some of the information I can already start going calculating some of that stuff. So yeah, there are different techniques that can be used there. But yeah, for this example, I mean, I was trying to basically mock out the database parts and just kind of show, um, there is a lot of data that has to be retrieved in a small amount of time in order to make a good decision, and so you definitely need some kind of a good mechanism to get that data there.
That's a
Uh,
great. The second one, how easy is it to migrate from Microsoft SQL to CockroachDB? I think one of the things to call out, there are a couple things to call out. First, we have some of our own migration tools that are built in with CockroachDB that allow you to make the transition not just from SQL Server, but from any other transactional database to CockroachDB, whether it's a schema conversion tool or a live migration service. There are some tools that are built into the product to allow you to do that. Second, we have a very agnostic and open ecosystem that allows you to work with third-party tools, whether it's Click or Stream or some of the other, Amazon DMS, for moving data and migrating data between different databases. And I think, the ultimate answer to that, those, obviously contacting us and talking to us because we have a extreme depth of experience in actually migrating from different systems, including SQL Server, both from our sales engineering team, people like Jim, myself, and Alex, as well as our professional services team.
Yeah, answer a few other questions here, just on the keyboard here, but um, and one question here, asking kind of what's the peak data volume rate you've seen in Cockroach? Um, I will say that we work with some customers who are publicly referenceable. We work with some who are not. Um, some of the ones that are we're not able to reference are moving a lot of transactions. Like some different industries get really spiky. Like one of the ones we can talk about is a company called Hard Rock Digital who does betting, sports betting, and you can imagine like leading up to the Super Bowl, the kind of throughput they need to handle huge sporting events like that. They have to be able to scale up really large, and they for betting and gaming you need very strong consistency, just like you do for payments. So that's an interesting example, I think. But we certainly do have some other customers that do financial trading and payment systems that scale to really large volumes. Well, I think that's all the time we have for questions. We're going to over a few minutes. Uh, if there are more questions, we'd love to get them and kind of answer them. If you can reach out with that contact form, I'll go back to that. Um,
There we
yeah,
go.
love to talk some more. Uh, we will send out a recording of this in the next few days. We really appreciate everybody attending and hope that this was good and helpful content to you. And I guess we will see you soon. Thanks for your attendance.
Thanks, everybody. Sure appreciate it.